Happy Thursday, everybody. Welcome back to COMP110. Today, we're going to be practicing diagramming in small groups. So if you haven't joined your house Zoom already, I would encourage you to join up. We'll get to that in just a little bit. The TAs made a check-in form, and the link is here, and I believe the TAs are going to be posting it in your house Zooms as well. This is an anonymous form just to get a feel for where everyone's at currently right now, just in general, and also with respect to 110. I think as the TAs and I have been discussing how this semester has been going for everybody, there's certainly a recognition that this is a uniquely strange semester in many ways, and that now that we're 2/3 of the way through, or closer to the end than the start, I think we've recognized that it's certainly been a very challenging semester. The isolation, the not having the ability to form study groups and actually work like with other people on whiteboards on certain questions. It's been a strange dynamic, but we want to check in, see where you're at. Where the TAs had some self-care tips that they're providing in this forum, and if you have some suggestions, we'd love to hear yours as well. But by and large, you all are doing an incredible job this semester, and I'm so impressed with the progress we've made so far. We are going to be taking some questions through Poll Everywhere as well. So if you want to open up Pollev and when we get to the points of working through questions, if there are things that we go over today that you want some additional clarification on, please do ask. The next quiz is Tuesday, and it'll be at 4:45 p.m. The focus of this quiz is going to be on the concepts we've been looking at since the last quiz. And there's no way around, as you've kind of been able to tell, making use of some of the concepts we learned earlier. So in a sense, this is a cumulative quiz because we're still going to have loops, we're still going to have functions, but the emphasis, the conceptual emphasis, will be on things such as references, which we're going to be going into even more detail on today, immutable heap objects. And again, that's going to be the focus of our diagramming questions today. We've spent a lot of time in the past couple weeks working with dictionaries, and they're a super handy tool for working with data in the way that you're doing that on the current problem set, or the current project, I should say, the weather statistics project. And if you haven't gotten started with that project, please do start immediately. The early deadline is tomorrow, and the regular deadline is on Sunday. Classes and objects were introduced asynchronously, and we're looking at the most basic form of classes and objects, ones that have attributes, and we'll get some practice with that today in diagram form. We probably won't have much in the way of code writing that involves classes and objects because you haven't really had a good opportunity to practice writing code other than the asynchronous content from Tuesday. But we will have some diagrams that involve them so that we start to get more comfortable with what the idea of classes and objects are. And then after the quiz, we'll be learning some additional concepts related to classes called constructors and methods. And we'll get much more practice working with classes and objects in our code. The format of this quiz will be slightly different because we will have some memory diagrams that will be drawn and handed in. So today we're going to get some practice, again, handing in memory diagrams via Gradescope. So the practice questions that we go through today, I'd ask you to try just getting in the habit of taking a screenshot of or using the PDF scanning application on your phone. I do think pen and paper is the best way to practice these because in other courses later on, you're probably not going to be on an iPad or a computer. But if you're on an iPad, that should work just fine too. There will be some code writing as well. The exact details here, we're still working out. This quiz is in the process of being written. As soon as I have a more firm sense of exactly, the timing constraints and things like that, I'll share it with you. Our intent is not to have time constraints like we did on the last quiz, but with the memory diagrams, we may constrain that a little bit so that we can get those questions asked at the first part of the quiz when we're able to ask clarification questions perhaps. And then the extended time would be more for code writing because that's where you've got more time. Good question. How would the memory diagrams be graded? So the way we go about asking for memory diagrams is we're looking for effectively correctness. And there are questions that we might ask in association with a memory diagram. And I'll give you some examples of what those might be today. But like how many objects are in the heap after this program, throughout the course of tracing this program, for example, might be one, or how many stack frames did it take to completely evaluate this program. There's some questions like that we might ask about your diagram to just sense the correctness in that way. And then we'll take a look at, are your arrows going to the correct places, things like that. All right. So before we get into the practice of working through these diagrams, there is one more concept that's a new concept, but it's a very simple one that I want to give you because it actually will simplify your lives. And it's a really nice piece of syntax that modern Python has available to us. And this concept is called, let me get to the right slide deck here, format strings, or more formally, you might know of this as string interpolation. So string interpolation with F strings in Python, or format strings, will give us a much handier way of writing concatenated strings than what we've been able to do so far. This is a feature of modern Python that most other modern programming languages have as well. When you're building up a string value in Python, what we know is that if you're concatenating a lot of values into a string that you're building up, it can involve a lot of syntax and work, right? Especially when you're concatenating things that aren't already strings, right? When you're trying to concatenate an integer into a string, you're having to convert that integer to a string first using the string constructor function, and then concatenate that value in. Well, there's a special syntax in Python called a format string, and for short, we refer to this as an F string, and you'll see why in just a moment, that doesn't give you any new capabilities, but it will make your life and your code much easier to read, right? It'll make your life easier and your code easier to read. So let's look at an example of this, and then we might try this out in the REPL really quick as well. So in this example, we've got actually, let's just go ahead and do this in the REPL. So Python, I'm gonna start a REPL here, and let me make this a bit bigger. And if I go ahead and declare a variable like course that's an integer and assign it a value like 110, we can print the concatenation of I am currently in, and then concatenate, and then we convert that integer course to a string and concatenate another exclamation point on the end of it, right? And so this should feel pretty familiar at this point in the course. I am currently in 110, right? And the syntax that we're seeing here, where you have to close off a string, so you have to terminate that string literal with a double quote, and then add your concatenation operator, and then convert your other variable to a string, is a lot of ceremony for doing something that should be a little bit more straightforward. And so let's take a look at how you would do this with an F string. So print, and then we use the character F just before our double quote. And this is what makes it an F string, right? So that's where the name is derived from. And I am currently in, and then we can use curly braces here and say course and an exclamation point, all right? And these curly braces are saying, hey, what is inside of these curly braces is a Python code expression. And what I want you to do is evaluate that expression inside of those curly braces as if it were real Python code, in whatever that expression evaluates to, convert it to a string, and then concatenate it right here in my string. So notice these two print statements did exactly the same thing, but this one was much shorter and a little bit easier to work with, all right? So how do we formalize the idea of using an F string? What were the steps that we took? Well, with a string literal, if you put an F before it, that's what characterizes it or classifies it as an F string. That's what gives Python the hint that, hey, what's about to come is a special kind of string, a formatted string. Then inside of that string, you can surround expressions in curly braces, and you can have more than one expression in your string as long as each one is individually surrounded in curly braces. And we'll take a look at this as an example in just a moment. All right, so let's try out one more example like this, where we can have someone's age, let's say an integer like 20, and someone's name, let's say a string like the example on the slide, I think used the name Lauren. and we can print an F string. Let's do a regular string first, just to remind ourselves of how much more work it is. So concatenate up a string like, hey, name, concatenate, you will soon be, and then stir of age +1. All right, and we can just leave it at that. So, hey, Lauren, you will soon be 21. And notice we were able to use an expression, a numeric, an integer expression here, where we're adding 1 to age and then converting it to a string and concatenating that in. So we could concatenate 2 values into the string that we were building up and printing out as part of a larger expression. Well, with an F string, we can say printf, hey, name in the curly braces. So notice the first thing we did to make the F string was we put the F before the double quote. And then the expression that we wanted to effectively insert at this point, or inject or concatenate, if we were using that concatenate operator like we did above, you will soon be, and then age +1, right? And notice that we could include 2 expressions in this F string literal, and we're able to write real expressions here. So notice this was evaluated to not just the name or the variable age, but we're adding 1 as well. And these values were automatically converted to strings on our behalf. We didn't have to explicitly convert age +1 to a string. That's just implicit in the idea of how an F string works. So when that string literal is evaluated, just like we've talked through, the expression is evaluated within the curly braces, then that's converted to a string, and then that's concatenated into the literal when the program reaches that point. This concept is more broadly known as string interpolation, so you'll see this in many other modern programming languages as well. The specific details will be slightly different, like that leading F character is very specific to Python. You won't see that exact same concept anywhere else, but most programming languages have a way of doing something like this, of producing string literals where you're inserting expression values without having to go through the hoops of concatenating and converting every value that you're injecting into that string. There are some more powerful things you can do with F strings in Python beyond what we're talking about here and sort of beyond our scope in this course. But the documentation that's in the slide deck it's worth reading through if you're curious about what else you can do with it. So that's a quick introduction to using string interpolation with F strings in Python. If there are any questions, go ahead and ask away. Otherwise, we're going to get into practice diagrams next. So if you can go ahead and get out a sheet of paper or have ready your diagramming tools, then we'll get started on that in just a moment. I'm not seeing, let's see. Great question. So there's a question here that is, should we make sure we don't use a variable f so that we don't start it with, or so that it doesn't get confused with an f string? Well, it turns out that you can use a variable named f, and Python will be able to distinguish between those two things. Those won't be the same. Let's see. There's a question about quiz review and some quiz concerns. I'll come back and talk about that at the very end, but there is a link on the course page that if you have specific questions about the quiz, we're going to be putting together a FAQ like we normally do. The TAs are going to be putting that together, and based on the questions that are asked in that form, we'll be answering them there. There will be some more practice problems and quiz material available as well. All right, so what we're going to do next is go ahead and practice diagramming with classes and objects. All right. And this first example, this first question, before we go into groups, I want to just get you set up with this problem so that we don't, so that we have covered how you represent a class in your in your diagrams. All right, there's one more question that just came in. Can F strings only be used for strt, int, and float? No, you can use it with any value you'd like. And what it will do is convert that value to a string. And in the next unit, as we get into talking about objects and classes with a little bit more depth than we're going to for today or for the quiz, we'll learn how we can add the ability for the classes and the objects that we make ourselves to be converted to strings automatically by Python so that they would have a nice string representation. If you try to convert just a random object to a string without adding anything else to our classes, you'll just get some sort of unhelpful output. It'll be like, this is an object of type fraction or something. But we'll extend that later. But you can use any value that can be converted to a string in an F string. That's a great question. All right, so let's start this diagram together, and then I'll turn it over to the TAs to get you all set up into breakout rooms. So in this question, we've got a class, and we haven't talked about, well, how do we represent that in our memory diagrams? So I'm going to go ahead and set up some space on my stack, or set up my stack and my heap. All right. And the stack is where the names and the values of our local variables are stored, as well as our globals frame. So by default, we're in our globals frame. And when we reach a class declaration like this, and a class definition, we're saying, hey, there's this class named frac. So the name frac in the globals frame, this is short for fraction, is going to be bound to the definition that's stored in the heap. All right, so class and 1 through 4, the lines that it's defined on. And this just lets us know where we would go back to look to see, what do we mean when we use the word frac. And so we're talking about a fraction here. And because we're diagramming this, one of the things that you'll see us do intentionally, and not necessarily as a good practice, but we probably should have named this numerator and denominator. But for the purposes of diagramming, I've shortened this to n and d so that the amount that we have to write in this diagram is a little bit less. All right, so that's our class fraction. Then we see our main function. So our main function is the function defined on lines 7 through 12. And the add function is the function defined on lines 15 through 19. All right. So now that we've got this set up, we reach the if statement, and this is our idiom. And when we're diagramming listings like this, we assume that the name special variable is assigned main. We've started the program in the right way, and this jumps into the main function. We have a function call to main. So let's go ahead and set up the function call to main. The return address is line 23. That's where we would go back to when the main function finishes up. There are no parameters to set up, right? So just to get you started on the right foot, and then in the next problems, I'll leave this entirely up to you to complete on your own. Let's go ahead and set up this object and these two attribute values, and then I'll turn it over to you all to work on this in a group. So we see a constructor call. And when we see a call to a constructor, this looks like a function, but we know that sort of with a hint that, hey, let's go find what is frac. And okay, we go in the globals frame, and frac is bound to the class that's defined on 1 through 4. So when we use a class name as a function call, like we are here, what we're doing is we're constructing a new object. And whenever we construct a new object, we set up an object space for it on the heap. So frac is the type. And frac is made up of two attributes, n and d. All right. Neither of those have any initial value associated with them. But this is how I'll represent a frac object on my heap. I'm going to put the name of the class at the top of a table, the names of the attributes on the left-hand side of these rows, and then the values that those attributes are bound to will be over here. All right. So we've set this object up, and once an object is constructed, what it will effectively return or give back to whatever it's going to be assigned to or however it's used is a reference. And so now A is going to be bound to this fraction object, right, in the main frame. And what we're saying here is A refers to this fraction object that was just constructed. And so now when we later reference A.n is assigned a value of 1, well, this left-hand side is saying, okay, do we know what A is? And yes, A is the variable in our main frame that refers to this fraction object. When you see a dot, what we're saying is follow the arrow and go look up something in this particular object. And we're looking for n. And we're saying, okay, this value in n is being assigned 1, right? And same idea with d, the denominator is going to be assigned a value of 4, right? So the same concept here. And now at that, we've reached line 11. And this is where I want to turn it over to you all and the TAs to set up breakout groups for you to talk through what happens next here. On this line, we're going to make a function call, and the result of that function call will be bound to B, and then we're going to print out an F string. So your goal here is to complete the rest of this diagram with your group, and we'll come back and talk about this in just a moment. So TAs, go ahead and take it away from here, and we'll have another 8 minutes or so on this. 2 more minutes on this, and then we'll come work through this together at 5:17. All right, great work thinking through this. So there are some interesting issues that we need to discuss that may have caused you a moment of pause and question as to how they work when it comes to using objects as the arguments to a function call. And to dive right into this concern, when we see on the right-hand side of this assignment statement that we're calling the add function, well, first we should probably see, do we know what add is? We don't see the word add defined in our main function frame, but we look in our globals frame after that, and we see that, okay, add is the function defined on lines 15 to 19. It takes 2 parameters, both should be of type fraction. Well, a is a value of type fraction. We're using it for both arguments. It seems like this function call is valid. So let's go ahead and set up a frame for the add function call. So add, and the return address that we'll go back to with a result is line 11. And we have 2 parameters to set up. LHS is the first parameter, and RHS is the second parameter. These abbreviations are often used in computer science, short for left-hand side and right-hand side. And if we're thinking about adding 2 fractions, we're kind of thinking about talking about the left-hand side of the addition operator and the right-hand side of the addition operator. We're just using these as the parameter names in this case. So what are we assigning to LHS? Well, we're assigning A to LHS, right? It's as if before this function call evaluates, we're saying LHS is assigned A. Well, A is this reference to this fraction on the heap. And so when we assign one reference value to another reference value, so A is being assigned to LHS, LHS is also going to be a reference to the same fraction object. We're not going to create a copy of this object. We're not going to create a new fraction anywhere. Just like when we passed lists in the previous hands-on example where we were working with these diagrams, objects, just like lists and dictionaries, are reference types. So we're always referring to some actual object on the heap. We're not actually copying it or doing anything like that. So here we're saying LHS is a reference to that fraction. And then the same idea with the second argument here, right? So the second argument is A, it's being assigned to RHS. So A is this reference, this pointer arrow to this fraction object. So RHS is also going to be a pointer to that fraction object. Notice the arrows are pointing to different places in this object, and that doesn't really matter. Where the arrows point is irrelevant to our concerns. We're referring to this whole fraction object in each of these cases. All right. So we jump in to this function. We've set up our parameters and we're ready to start processing this function. And this first line here is setting up a new fraction, right? So this is a call to frac. We don't have the word frac defined anywhere in this frame, right? So we look in our globals frame next and we see, is there something named frac there? Yes, it's the class. So we're using a class name as a function. So we're constructing a new frac object. We're going to have another frac object on our heap, and it's also going to have attributes n and d. So let me go ahead and set up this object here. And it's not going to have any default values associated with its numerator or denominator, right? And a reference to that object is what the call frac evaluates to, and that's what's going to be assigned to the word res here. So res is going to have a reference to this object, right? Now there's a question that came in earlier that was, on a line like this, why do we use this colon frac here? Well, remember, when we declare a variable for the very first time, we often will establish and very explicitly state what is the type of this variable. Now, once we're comfortable with the idea of type inference, we could omit this information, right? But if we wanted to be explicit and and be sure that we're not making any type errors, there's no problem with saying res is going to be a variable that holds a reference to a frac object, right? Just like we could have said x is an integer that holds the value 5 or something like that. Why it's a little bit funky or different from what we've seen before with integers and string literals or strings and things like that is because we see this sort of repeated word here. And when we're working with objects that are objects we defined, right? We invented the idea of what a frac is at the very top of this listing. We have to construct that object for in order to use a value of that type. So we have to call that constructor function explicitly ourselves. All right. I'm going to go ahead and open up questions again, and I'll keep working through these next couple of lines and then take questions on this diagram in just a moment. Right, so this next line has a big expression in it, right? And what we're doing here is we're just trying to add up to fractions, and it turns out that both of those fractions are the fractions whose numerator is 1 and denominator is 4, right? So how do we do this? Well, LHS.n. What is LHS? LHS is this object whose n property or attribute is 1. So LHS.n is 1, and I'm just going to scratch up top here 1 multiplied by RHS.d. So RHS is the same object. Its denominator or d attribute is 4, and then plus, and RHS.n is 1, and our LHS.d is 4, right? And that's a multiplication 4, all right? So this is 1 times 4 plus 1 times 4. Thanks to orders of operations, we know that this is going to just evaluate to 8, right? Right? And so the numerator here will be 8. And the denominator is just the LHS.d. So LHS.d is 4, and RHS.d is also 4. 4 times 4 is 16, right? And so 8 in the numerator and 16 in the denominator makes sense when we're trying to add 1/4 plus 1/4, right? This is what the problem we're modeling. And so now we are about to reach this line right here, but a question's come in. So let me address that before we continue on. So I'm pausing at line 19. So this question goes back to this statement here, which is, what is the difference between colon frac and this function call frac? So this is thinking about what are the differences between these two things is important, right? So let me give you one more example that I think actually illustrates this, and you've seen it before, right? So earlier, we could say something like x is an integer, and it's assigned integer of string 5, right? And so typically we would just write, x int is assigned 5, right? Because there's this idea of a number literal or an integer literal that we can write directly in our programs. But we've also seen cases where we've used the integer constructor and constructed an integer from, say, a string that allowed us to produce an integer representation of the string 5 that we could then assign to this x variable. And so what comes after the colon here is the type. We're saying x is type integer. And if we looked at this example down here, we're saying The variable named res is of type frac, and frac is the class that we're defining. Remember, when you define a class, you're defining a custom data type. And when we say frac constructor here, that's actually constructing a new frac object on our heap that we can then work with and use. So that's the key difference between those. Does it matter how you have the LHS res in vertical order? Good question. So by convention, I am going to keep the local variable names. So that includes parameter names. So LHS and RHS were parameter names of this function. And then res was the name of a variable we're setting up that's a local variable inside of this add function. And I'll tend to keep track of those in my right-hand side of a frame. And I'll just add them to the frame in vertical order by a convention, but that's not necessarily important. I do think it's important typically to differentiate that from the return address and the return value, because those, notice that these names are things that have meaning and are bound to values in our programs, whereas return address and return value are sort of the bookkeeping we're having to keep track of in order to trace through our program. So you couldn't actually access here like the RA, it's not a variable that exists in this frame. That's just extra information about how we're processing this program. Can I explain why the RA for add is 11 instead of 15 or 19? Sure. Great question. So the definition of add begins on line 15, right? And when we first trace through and set up our names in our globals frame, add is the function that exists from lines 15 to 19, right? So that's where the definition is. But what the return address is, when we actually use a function like add and we call it, right? The function call, the reason why we jumped into this function to begin with, that occurred on line 11. And so with the return address, what we're keeping track of is where will we go back to with a return value? And we'll see that in the very next step, right? If we don't set a value for n and d as integers, is the class, sorry, I cuts out just before definition, do they have default assignments like 0? They are undefined. So if we don't add any default values in our class definition here, these values are undefined. If you tried to access them directly, you would get that attribute is not defined error. Why don't we add B to the main diagram? So we're actually just about to get to that question. And let me just parse through these next few questions and be sure that there's nothing that needs to be addressed first. But we're going to add B next, right? We're just about to return from the add function. This is the line we will process next. If you assign a variable to an int attribute of an object, will it use a reference or will it store the value separately? Good question. So this question is a little bit nuanced. Let me come back to this question. I'm gonna mark it. Let me come back to this question in just a moment once we've actually finished processing that. All right. Why don't LHS and RHS point to the new frac box? Okay, this is a good question. So LHS and RHS were established when we called this function, right? So A is what we assigned to LHS and RHS. We never changed LHS and RHS in the process of the add function, right? We've made it down to here. If somewhere we had said something like LHS is actually a new frac object, right? Or something like that, we would have reassigned it to be refer to something else. But the only way one of those arrows would change is if we saw something like LHS is assigned something else, doesn't actually matter as long as it's a frac type. The only way that we would have changed one of those arrows is if we had reassigned one of those variable names. But notice, we're not reassigning on any of these assignment statements, either of those variables. We're changing, first we're setting up res to refer to this new frac object, and then we're updating the attributes of res to be these computations. All right. Good question. So I put LHS.n and LHS.d in the add function frame. Do we not need to write this? So technically, those two values don't exist in the add function frame. When we use a name like LHS.n and RHS.d, those are values that are stored in this frac object, and we're actually looking those names up in this frac object. So the name LHS exists in the add frame, right? But when we use this dot, what we're saying is go look up in some other object, whatever object we're referring to, look there for this given attribute. And that attribute only lives there. We haven't established anything of that same name in the add frame. There's no copy being made. And so I will give an example because it's related to the question I said I would come back to of what happens. Actually, let me just address it right now because this is a good setup for it. So let's imagine, I'm going to imagine this line's gone for just a second. Let's imagine we had something like n is assigned, or n of int is assigned LHS.n, right? So we have to evaluate the right-hand side of a statement first, of an assignment statement, right? So LHS.n is 1. So it's as if this is 1 is being assigned to some integer named n. So we'd have an integer named n on this frame in the stack, and its value would be 1. There is not a reference that's kept to the n property or the n attribute of that object. If we were to do something like this, this is an integer type, so we're going to make a copy of that integer value into our frame here. All right. So the next question, and this is the last one I'll take before we get into this return statement, and then I'll come back to any remaining once we finish tracing this. But why are there 2 frac objects in the heap instead of 1? Well, remember here, we set up our first one, right? So you can almost count the number of times you see the name of a class constructed and the processors reach that line to evaluate it would relate to how many times or how many objects there are in the heap. The first frac came from this line evaluating. And then when we reached this function call, we jumped into the add function, and the second frac was evaluated here. The only way that you're going to get a new frac object on the heap is by calling this frac object or this frac class constructor, right? All right. So now when we get to line 19, let's finish this out. All right. So we've just finished computing the res objects numerator and denominator, and we're ready to return res. This is the statement we're going to complete from this point. So what is res? Well, res is a reference to the fraction that we've just constructed, whose n is now 8 and d is 16. So the return value of this function is going to be a reference to that same frac object, all right? So we return a reference. When we say that we're returning something of type object, what we're actually returning is a reference. So where are we sending this reference? Well, this is why we keep track of the RA. So the RA is 11, and we're saying send that reference back up to line 11, which is where that function call was encountered, and assign that reference to this new variable we're setting up named b, right? So b is going to now be in the main function frame, and it's going to refer to this new frac object that we just constructed as a part of calling that add function, all right? And so this line, once it's completed, will result in the variable b in main's frame being bound to this object whose n is 8 and d is 16. All right. So then when we finally call this print statement, we say, okay, this is a format string. So it's like we're concatenating or building up a string. B.n, so b dot, follow the arrow is the dot, n is 8. So 8 over is the forward leaning slash there. And then b.d, b dot, and d is 16 would be the string that was printed to output. All right. Next question is, if you changed a value for LHS or RHS, would you have to make a new frac, or would you change the values in the same box? All right, this is a great question. Let's imagine we are in main. All right, so I actually haven't finished this program out completely because we didn't return from main, right? We should have had a return value of nothing in main, and we would have continued on and the program would have finished. But let's imagine here we said A is assigned B for a second, right? So A takes the value of B, A is bound to B. Well, what is B? B is a reference to this frac whose n is 8 and d is 16. So in a statement like this, if we saw this statement, we would say, oh, A is no longer bound to this fraction where n is 1 and d is 4. A is bound to the same fraction as B is, right? That's what this would have evaluated to. I'm going to reset this back to how we had it before and want to consider one other option here. What if we said A is assigned a new frac object at this point? Well, if we reassigned A to a new frac object, we would need to establish a new frac object somewhere on our heap. And I'm kind of out of space, so I'm just going to draw it up here. You can believe me when I say that this is supposed to still be on the heap that would have its own n and d. Neither would be initialized. And we would assign A to that new frac if we saw this line in main. All right. So you can reassign variables that are bound to objects. And when you see an assignment statement and a variable that refers to a reference type, for example, an object or a class like frac, we're going to be updating references. So let me reset this back to how we started or where we should have been and finish this out. And then there's two other questions, it looks like. All right, so we reached the end of the main function, and we know that because there's no more lines, and we unindent and we see the next function definition, so we've reached the end of main. So we would return none, right? And I tend to represent none with this empty symbol slash through it, but you could write out none if you wanted, back to line 23, right? So that's where this program began from. And if we had any additional code after line 23, we would have gone and evaluated that next, but we don't, so our program is completed. All right. So another question, could you also use a dictionary with keys n and d and values 1 and 4? This is a great question. And this particular problem actually highlights a place where we get some benefit from using a class. So the short answer is yes, you could use a dictionary with keys n and d and assigned values that are integers, and your dictionary could have keys of type int, or sorry, keys of type string and values of type int. But it's what it ultimately turns out is that if you wanted to write a program like and you have this add function, you'd be adding an LHS of dict where stir and int is the type, right? And same with RHS. And notice that this doesn't actually give you a guarantee that that dictionary is going to have the keys n and d in it, right? And maybe in your program it does, but if you wanted this add function to be one that other people could use and make sense of, you don't have that guarantee. You would be trusting on faith that someone who called this function just was very careful to be sure that every dictionary they called this function with had those two keys established in it. Whereas with classes, right, we're saying here, we're making a much stronger statement, and we have much more trust that no, if in order to call this class, you have to give me two frac objects, and you know that they should have those two values associated with them, right? And because we're always going to assume that we fully initialize our objects, and we'll learn some new ways of doing this and guaranteeing this after the quiz. But here we're initializing those attributes. So when we realize that, we've got a much better program, or a much better stated program. All right, so would 8 of 16 not automatically simplify to 1 out of 2 because it is in a string? No. So if we wanted to have some simplification, we would need to add that extra bit of functionality ourselves. And that's actually a good exercise. You would need to calculate the least common denominator, divide them by the least common denominator, and be sure that you've done that. But notice, like, the fraction that we returned was an object that had an n attribute of 8 and a d attribute of 16. And the computer is kind of not very smart, right? Like, it's not going to do anything other than exactly what we tell it to do. And it's not going to like jump to any conclusion without us writing the code for it to be able to do that. And in this case, it's just going to print out exactly what we asked it to. And what was stored in the n attribute was 8 and in the d attribute 16. Now, it would be a great exercise, and I would encourage you, if you want to go try coding up a fraction that after calling an add function like this automatically simplified itself, that's a great exercise. And it's a great observation because I think this is one of those things that when you're learning how to program, it feels like, wow, is the computer really that simple-minded that it wouldn't automatically simplify this fraction for me? I mean, fractions were something I could simplify when I was, 10 years old. And the answer is no. The computer will not do that automatically for you. You have to program that in or use a library that does. All right. For the purposes of making sure that we have time to get through the next exercise, let's go ahead and jump to the next exercise. And I'm going to pause questions for now, and I'll take a look at these and address them as we come back. But let me go ahead and set up the questions that we'll be diagramming next. So this is an extension of what we just looked at, right? And in this extension, I'm not going to start it out for you. I want you to try starting it out on your own. And there are some subtle differences that will have some interesting implications in this program versus the previous one. So go ahead and try working with your neighbors through this. I'll turn it over to the TAs for breakouts, and we'll have 10 minutes on this. We'll come back at 5:50. One more minute and we'll talk about this together. All right. I know some of you may not have been able to work all the way through this, but for the purposes of trying to finish up in time for the end of lecture, let's go ahead and talk through it. So I've gone ahead and set up the globals frame as well as the main frame, and we've called main from line 24. These set of lines where we set up variables A and B to refer to new frac objects. So notice each time we call this frac constructor, that results in a reference to an object on the heap. And I went ahead and initialized the property or the attributes of those objects on these lines. So now we have a frac with 1 and 2 and a frac with 1 and 4. There's a question in the previous problem where someone asked, why can't we just do a frac of, say, 1 and 2 here, right? To set up a frac where the n would be 1 and the d would be 2. Well, in the next unit, we're actually going to look at how we can extend our definition of what a frac class is made up of so that we could do something like this. But as this class is currently defined, we can only construct it in this way. We can't, this wouldn't be valid. You could try it, but we need to learn a new concept, which is what we would call a custom constructor. Right now, we're using the default constructor, and that's just going to set up any default values. Here, there are no default values. All right. So now we reach this call to add of A and B. And we look at our add function, we see that, okay, it's got a same signature for the parameters. Left-hand side is a frac, right-hand side is a frac. So let's go ahead and set up this function call. So we have a function call to add, and the return address is going to be line 14. Right, so the return address is the line that the function call occurs on, and it occurred on line 14. That's where we're going to leave our bookmark. We're going to go back there once we're done with this function, and we have an LHS parameter to set up and an RHS parameter to set up. Okay, so LHS is being assigned A, right? So A is a reference to the frac whose n is 1 and d is 2. So LHS is also going to be a reference to that frac, and the second argument, B, is being assigned to the parameter RHS. So RHS is going to be whatever B is. And so B was a reference to this frac 1, 4. So RHS is going to be a reference to that same frac. All right. And now we're ready. Once we've established our return address and our parameters, we're ready to jump into this function definition. So we jump in and we see this kind of gnarly looking statement where we've got to go compute how do we add these up. Well, let's break this down. So LHS.n. LHS dot, we follow the arrow, n is 1, so 1 multiplied by, and then RHS.d is RHS.d is 4, plus, and then RHS.n is 1 multiplied by LHS.d is 2. All right, so we are once again just going to do some basic arithmetic here. 4 plus 2 is going to be 6, right? So this expression evaluates to 6, right? And now if we were to think, well, this is the same as saying LHS dot n is assigned 6. So what does it mean to have an attribute assignment on the left-hand side of an assignment operator, right? So this is what we're trying to evaluate here. Well, we look up LHS dot, follow this arrow, n is this value 1, and we're actually changing this value to be 6, right? And now what we're going to need to do is carry on to the next line, right? So on the next line, we see that LHS.d is 2 multiplied by RHS.d is 4 so that's going to be 8, right, is going to be assigned to LHS.D. So LHS.D is going to be 8, right? So this is the same as saying LHS.D is assigned 2 times 4, or 8. And so we're updating LHS.D. So now LHS's N and D are 6 and 8, respectively. And we've reached the end of this add function, and it returns none, right? So this doesn't actually have any meaningful return values. We add the RV of none to our diagram. And where do we go back to? Well, we go back to line 14. We just finished line 14. So we've completely evaluated line 14. And we're ready to print out what is A.N and A.D. And in this case, well, notice that in the add function, we actually changed A's attributes to be 6 and 8. So when we print out A.N, that would be 6 over 8, right? And that would be the string that gets printed out. And then we reach the end of this main function. So the return value is going to be nothing. And I should have closed this box off. So the return value of main is nothing. We go back to line 24 and the program's completed. There's a great question in the previous set of questions that is it safe to say that each frame on our stack is going to have both a return address and a return value? And yes, for the program to have fully completed, each frame will have both a return address and a return value. All right, I'm going to activate those questions again, and I'm happy to take some more questions here. In this case, in this particular diagram, we're emphasizing this idea that because we're actually giving another function like add a reference to some object, in both of those references, so LHS and A referred to the exact same object, if we change something about that reference, so we changed LHS is both of its attributes, well, that change is going to be carried through or visible when we return back to some other frame, and we've actually changed A's attributes in the add function call because both of them, both A and LHS, were referring to the same object, right? We didn't construct any new objects in add. Why is LHS the first frac and RHS the second frac? So notice in this call to add, so A was assigned a frac, and that was the first frac, and B was assigned a new frac, and that was the second frac. In this call to add, we're passing A to LHS and B to RHS. So that's why A was the first frac we set up, B was the second frac we set up, and so that's why LHS and RHS were bound to the fracs in that way. Great question. All right. When we were changing the value of something in the stack or heap, do you think it makes sense for us to erase the old value or cross it out? I tend to think that if you're working on paper, it's probably easier just to cross it out. With the exception arrows, your arrows, if you start crossing out arrows and reassigning them, you start kind of looking like that meme of like the crazy guy. I think it's, I'm now forgetting the show that's from, but the conspiracy theorist with arrows everywhere. And so I tend to think that with arrows, if you can erase them and reassign them, that's great. But with values, if you want to cross them out and just write in new values, that's fine. Should we include print in the stack? Yes. So I should have done a better job of so that's a great question. How should we include print? So typically I would have either a box somewhere or a third column for my printed output. And we would have printed output would be A.N was 6 over 8 was what that F string evaluated to. And that we would have had an output column. Yes, so good question here. Let me take, this will be the last question on this diagram, and then I want to talk about the third diagram that we're not going to get to, and that I'm not going to ask you to submit, right? So good question here. Yes, oh, thank you. Always sunny in Philadelphia. Yes, thank you for correcting me there and providing that. Yes, always sunny. Love that meme. Okay, so what does this F string actually evaluate to if we were to try and write this with concatenation? Well, A.N and A.D are both integer types, right? So if we want to include them in a string, we're going to have to convert them to string values. And so if we were to try and make this with string concatenation, we would have alternatively written print, and we would have had to say stir of A.N concatenated with the string with a // concatenated with, I'm kind of running out of space here. Let me just write this down below, or yeah, I'll just write this right here. I think there's actually a way for me to maybe, that's a little scary. That blacks out my entire screen, so I don't think that would, I don't know if that actually works. Stir, and I'm just gonna delete this. Okay, if you need to go back to the diagram, just rewind the video, and let me just write this out fully. So stir of a.d, right? And then end parenthesis. So notice how much more we would have had to have written using string concatenation and converting those values to strings. All right, great questions today and great work on these diagrams. There's a third diagram in the slide deck. And what I'll do is, because we didn't have time to get through it in class, and I don't want to expect for a lesson that you need to take time after class to complete it, I've gone ahead and on the grade scope entry for today for uploading and getting practice uploading these diagrams. And we won't check today's for correctness. We're just gonna be looking for completion and being sure that everyone is comfortable with uploading a response to these kinds of questions, because we'll see them on the quiz. But for this particular question, as soon as we get off this call or this class, it's so weird to be teaching remotely. I would much rather and would love to have seen your beautiful faces in the classroom. But I'll record a walkthrough of this particular problem. I would encourage you, when you get a chance, to try it yourself before watching the walkthrough, but I'll get that posted to the website as well. In addition to these, the team of TAs that's working on review questions is going to have some that are even more challenging than this, and that when I looked at them, they looked even more challenging than I anticipate us having on the quiz, so they're very good practice. But this one will practice with dictionaries and lists, and I'll get that video uploaded to the course site very soon. So that's all we've got for today. This was practice with diagramming. We do have tutoring hours just after class, so I would encourage you, if you have questions on these diagrams, tutoring is the best place to come for practicing, asking more in-depth questions. There are some questions that were a little bit beyond our scope in 110, like talking about SQL. And if you want to work on this third question in tutoring, I think TAs would be happy to assist you on this question and help you work through it there as well. So great work today, and we will have some additional guidance on what you can expect on the quiz, formatting and whatnot, a FAQ coming up very soon. I'll shoot out an email via Sakai, so look for that in the near future. Otherwise, do continue working on the weather statistics project and enjoy your weekend.